welcome to the next teaching unit in the chapter Photovoltaic System Design, which is about calculating the yield of a PV system. How can we estimate the yield of a PV system? An essential parameter for the calculation of the energy yield is the annual irradiation on the generator surface. This is usually determined on the basis of long-term average values of the horizontal global radiation, the annual global horizontal irradiation in kilowatt hours per square meter, from which the annual irradiation on the tilted module can be calculated. To calculate the annual irradiation on the tilted surface, the following calculation is performed for each hour of the year. From the hourly weather data, the direct and diffuse radiation component of the horizontal radiation is calculated using physical models. To calculate the direct irradiance on the tilted surface, first the solar elevation and solar azimuth are calculated. Together with the azimuth and tilt angle of the modules, the angle of incidence on the module and the direct or beam irradiance on the tilted surface, BTI, can be determined. When calculating the diffuse irradiance on the tilted surface, physical models are used which take into account the distribution of the diffuse irradiance over the solid angle. In addition, the ground reflection is also calculated. An albedo of 0.2 is often used as the default value. From the direct diffuse and reflected irradiance on the tilted surface, we get the global tilted irradiance, GTI. Finally, the GTI values are summed up over all hours over the year. This results in the annual GTI, the global irradiation on the tilted surface over a year. While the GTI is a power density in watt per square meter, the annual GTI is an energy density in kilowatt hours per square meter. There are many online tools that can be used to estimate the amount of annual global radiation on the tilted surface. One example is Enrol's PViTeach tool, which can also be used to make rough yield estimations of PV systems. But how can we estimate the height of the annual GTI if we don't have a suitable tool at hand? In addition to the orientation and tilt of the module, the latitude of the installation is also of great importance here. Here you can see the ratio of the annual GTI to the annual GHI, global horizontal irradiance, for different orientations and tilts on the equator, that is the latitude 0. It can be seen that the solar yield on the tilted surface is never greater than on the horizontal. The horizontal corresponds to a tilt angle of 0 degree. In this case, the x-axis. If we move away from the equator, the situation changes. At the 15th latitude, the annual GTI is already 3% higher than the annual GHI at an angle of inclination of 15 degrees. When increasing distance from the equator, the ratio between annual GTI and annual GHI and the horizontal surface becomes even more extreme. With the help of these diagrams, the height of the annual GTI can be estimated from the annual GHI for a given system site. For example, let's assume we would like to calculate the annual GTI for a plant located at latitude 60, which is inclined at 40 degrees. For this plant, the annual global irradiance on the tilted surface is approximately 115% of the annual global irradiance on the horizontal surface. Note that these diagrams are not universal. This is because diffuse radiation also has a large effect on the annual GTI. If a global radiation throughout the year consists of diffuse radiation, then even for a PV installation on a latitude of 60 degrees, the horizontal orientation would be optimal and the annual GTI would decrease with increasing tilt of the modules. Once the annual GTI is known, we can calculate the yield of an ideal PV plant. Ideal because we first neglect all losses that we might still occur in the system. To calculate the ideal energy yield, we multiply the annual GTI by the efficiency of the module and the generator area of the system. Here we use the well-known equation for the efficiency and can simply simplify the calculation a little bit. The ideal energy yield is the irradiation on the inclined plane times the installed PV peak power divided by 1000 watt per square meter. As an example, let's consider a system with a nominal power of 10 kilowatt. Since this power reflects the peak power at 1000 watt per square meter, it is also referred to as kilowatt peak. With an annual irradiation of 1100 kilowatt hours per square meter, the ideal energy yield is 11,000 kilowatt hours. In practice, it is common to normalize the yield to the power of the PV plant. Through this conversion, we obtain the so-called reference yield of the PV plant. The unit of the reference yield is kilowatt hours per kilowatt peak. By normalizing to the installed PV power, the reference yield is only dependent on the amount of annual GTI. In our example from just now, the reference yield is 1100 kilowatt hours per kilowatt peak. If we reduce the kilowatt in the numerator and in the denominator, the remaining dimension is hours. In a real PV system, however, a number of losses occur that reduce the ideal system yield. Most of these losses have already been discussed in detail in the previous chapters. In the following, we will summarize them. First of all, there are a number of optical losses that prevent incident solar irradiation on the module from being converted into electrical energy. For example, shading of single or multiple modules may occur. We have already seen that in a series connection, even the partial shading of a single module leads to considerable power losses in the entire module string. Estimating the amount of these losses is not easy. One possibility is to use special tools to draw the surroundings of the system in a sun-path diagram. This allows to roughly estimate the time period in which shading occurs. Here you see the already known sun-path diagram for a solar plant in Cologne with an exemplary shadow horizon. There's a tree in relatively close proximity to the plant, which leads to shading for several hours in the afternoon and evening hours, almost all year around. If it's a leaf tree, the shading will be significantly greater in summer than in winter, when only the tree's branches shade the plant. In addition, the influence of shading on the energy yield of the PV plant also depends on the system layout. For example, shading losses are lower when simultaneously shaded modules are connected in a string or even when power optimizers are used. The yield losses due to shading can only be estimated very roughly with the method presented here. For an exact calculation of the expected losses, the use of professional simulation programs is recommended. Here, either a self-created shadow horizon can be imported, or the expected shading can be calculated for every hour of the year using a 3D simulation. In addition to shading by objects, more or less severe soiling of the modules by leaves, dust or dirt must also be expected. This soiling is of course dependent on location and weather conditions. In areas with frequent rainfall, soiling is regularly washed away, so that only relatively low losses of 0.5% per year must be expected. At locations with long dry periods, especially if they occur in the sunny summer months, yield losses of well over 5% are possible. In addition to dust and dirt, snow can also reduce the solar yield, especially if it remains on the modules for a long time. Here, too, the losses are strongly dependent on location. In northern regions, where snowfall can be expected for several months of the year, they can amount to more than 20% per year. Last but not least, reflection of incident light occurs at the front side of the modules. The reflection can, of course, be reduced by an antireflective layer on the solar glass. However, the amount of light that is reflected depends on the angle of incidence of the light, even with antireflective coating. Shown here is the theoretical transmittance of a glass with an antireflective coating as a function of the angle of incidence. The transmittance is given in relation to the transmittance at perpendicular incidence. It can be clearly seen that only relatively low reflection losses occur at low angles of incidence. Above angles of incidence of 50 degrees, however, reflection increases significantly. The annual reflection losses will therefore be greater the greater the proportion of high angles of incidence on the module plane. How often high angles of incidence occur during the course of the year depends mainly on the latitude and the inclination orientation of the modules. Let us first see how high the reflection losses are for a PV system where the modules are oriented towards the equator and are optimally tilted. The annual losses for the glass chosen as an example here are between 1.5 and 2% and increase slightly with increasing latitude. This is due to the fact that the position of the sun at high latitude is undergoing seasonal changes and high angles of incidence are thus more frequent. This effect is increased if the orientation and inclination of the plant are chosen differently. Here you can see the annual losses due to the reflection for a plant with west orientation and a tilt angle of only 10 degrees. At low latitudes, the losses barely increase with respect to the optimal orientation and tilt angle. This is because the optimal tilt angle here is a few degrees anyway. At increasing latitudes, however, the reflection losses now increase significantly and exceed 3% for a system on Iceland. I would like to point out at this point that the annual losses shown here are not universally. Dependence of the reflectance on the angle of incidence varies with the glass, the selected antireflective layer, and if present, the texture of the solar glass. Besides the optical losses, there are several losses on the part of the PV modules. The most important factor which we have left out of the calculation of the ideal yield is the influence of the temperature. We have already seen in the last unit of this chapter that the actual power output of PV modules is significantly lower than under STC conditions due to the temperatures reached during normal operation. The decrease of the module power with temperature is described by the temperature coefficient gamma. For an average monocrystalline silicon module, it is minus 0.4% per degree Celsius. In the best case, it is below minus 0.3% per degree Celsius, but poor monocrystalline modules can also have values of minus 0.5% per degree Celsius. The best temperature behavior is shown by thin-film modules made of amorphous silicon or cadmium telluride. The temperature coefficient here is only minus 0.2% per degree Celsius. However, modules made of amorphous silicons are no longer used in PV systems because their overall efficiency at STC is much lower than that of crystalline modules. Modules made of cadmium telluride, whose efficiency is comparatively much higher than in the case of amorphous silicon, are still used to a certain extent in ground-mounted systems. Let's see what amount of annual losses results from the temperature behavior for an average monocrystalline module with a temperature coefficient of minus 0.4% per degree Celsius. In general, losses increase with increasing ambient temperature and with the magnitude of the temperature coefficient. At very low temperatures, the PV power can even be several percent higher than it would be under STC conditions. In very hot areas, however, annual yield losses of up to 10% must be expected. To illustrate the influence of temperature coefficients, let us now look at the losses for a good monocrystalline module with a temperature coefficient of minus 0.3% per degree Celsius. Especially in warmer regions, the better temperature behavior is clearly noticeable here. In the extreme case, there are now only losses of 8 instead of 10%. In areas with moderate temperatures, however, the difference between various modules is much smaller. In Cologne, where the annual average ambient temperature is about 11 degrees Celsius, the difference between the two modules is barely 0.5%. However, not only the module temperature has an influence on the efficiency of the module, but also the irradiance. As a reminder, the efficiency is logarithmically related to the irradiance and drops significantly at low irradiances. The behavior of a module under low irradiances is also called low light behavior. At 200 watt per square meter, the reduction relative to the efficiency at STC is about 4 and 6% for monocrystalline modules. A module with a nominal efficiency of 20% thus only has an efficiency of approximately 19% at 200 watt per square meter. The decrease in efficiency with low light causes yield losses, which are the greater the more frequently low irradiance events are to be expected. The frequency of low light events correlates with the annual irradiation at the module level. Shown here is the amount of yield losses due to low light behavior of a crystalline silicon solar module for 14 selected locations with different annual irradiation or annual GTI. For the module selected here, the losses are about 2% for an optimal oriented and tilted system in Cologne. In regions with very high irradiation, on the other hand, losses of only 1% are to be expected. For the sake of completeness, it should be mentioned that the spectrum of solar radiation also has an influence on the energy yield. The spectrum of solar radiation depends on many factors, including air mass, cloud cover, atmospheric composition, dust content, and many others. The amount of solar radiation that can be used by a particular solar cell varies with the spectrum. However, the nominal power always refers to the standard AM 1.5 spectrum at 1000 watt per square meter. With a different spectrum, the actual power of a PV module can be both higher and lower, depending on whether the proportion of the spectrum that is usable for the module increases or decreases. The losses due to a different spectrum are generally rather low, especially in relation to the annual yield. Next, let's take a look at the losses caused by the connection of the modules. On the one hand, there are the ohmic power losses in the cables and the electrical connections of the system. If the cables are correctly sized, the losses do not exceed 1% in the DC cables and 3% in the AC cables. The losses in the connections can be roughly assumed to be 0.5%. In addition, mismatch losses occur in the interconnection of the modules due to production-related difference in the electrical properties between the modules. We have already looked at these mismatch losses in more detail when connecting solar cells to form a solar module. The principles are exactly the same here. On average, the mismatch losses amount to about 2%. However, with good planning or clever sorting of the modules during installation, they amount to only 1%. For this, the currents in the MPP should vary as little as possible within a string. However, the mismatch losses can increase over time due to the different aging of the individual modules. Finally, we consider the losses of the inverter. First, we need to consider the efficiency of the inverter here. You know by now that the efficiency of an inverter depends on the input power and drops sharply at low power. Nowadays, however, inverters generally have a relatively good partial load efficiency, so that the maximum efficiency already gives a good indication of the losses to be expected. In addition, the dimensioning factor also plays a role here, as it determines how often clipping occurs due to excessive DC power. Furthermore, inverter and grid failures can lead to yield losses of the plant. Even if these failures cannot be directly attributed to the system design itself, they should be taken into account in a yield prediction. If a standalone inverter is used, the losses are lower, since the inverter can continue to operate even in the event of a grid failure. Let's take another look at an overview of all losses using the example of a system in Cologne. We have chosen the low values in each case. In a real plant, individual losses might be higher. In total, this results in a system efficiency of 82.5%. Taking into account the losses, the plant delivers the plant yield, E real. By normalizing the real yield to the normal power of the plant, we obtain the final yield. The unit of the final yield is kilowatt hours per kilowatt peak. Again, the kilowatt in the numerator and the denominator can be reduced to obtain the unit hours. The final yield thus indicates the number of hours that the PV modules would need at their rated power to achieve the real annual yield. The final yield is strongly dependent on the location. It can be used to compare system yields at different locations regardless of their size. Another important parameter is the performance ratio. It is defined as the ratio of the final yield to the reference yield. It thus corresponds to the coefficient of real and ideal energy yield. It is therefore a measure of the losses occurring in a plant. For good plants with low losses, the performance ratio reaches values between 75% and 90%. However, poor plants can also have values below 0.65. The reason for such low values can be, for example, high shading losses. In contrast to the final yield, the performance ratio is only influenced to a limited extent by the location and is more a measure of the quality of a PV system. We have now become familiar with a number of losses that must be estimated individually for each plant. While some losses, such as the cable losses, can also be estimated as a general rule, this is only possible with great inaccuracy for most other losses. A higher accuracy can be achieved by using simulation programs, which calculate the yield for each hour of the year. We have already seen at the beginning of this unit how the hourly irradiation on the tilted surface is calculated with such a program. Based on these data, a simulation program can also calculate the losses that occur. Professional simulation programs also provide databases for different modules in inverters and support the selection and correct sizing of the inverter and the connection of the modules. Let's summarize this teaching unit. The basis of the yield prediction is hourly irradiation data of the global radiation, which is converted to the tilted surface and used to calculate the ideal energy yield. In real systems, a number of losses occur, depending on the location and the selected components. The sum of all system losses is described by the performance ratio, which describes the ratio between real and ideal energy yield. For an accurate energy yield calculation, simulation programs are used. These contain databases of the different system components and support the component selection and the correct system design. I thank you for your attention.